Hello students, today I am here with a quick revision of the chapter Solid State. So let's get started. What is solid? Solid is that form of matter which possesses rigidity and hence a definite shape and a definite volume. Now we will see why do some substances exist as solids or cause of existence as solid. The physical state of any substance depends upon two types of forces. One is intermolecular force of attraction, which tries to keep the constituent particles close together. Second one is thermal energy. This energy is due to temperature. This energy helps to move the particles faster. So, thermal energy tries to keep the particles apart. When intermolecular force of attraction is greater than thermal energy, that substance exists as a solid. Now let's study classification of solids. Solids are broadly classified into two types as crystalline solids and amorphous solids. In case of crystalline solids, the constituent particles are arranged in a definite geometric pattern in three-dimensional space so that we can see short range as well as long range order of particles. In simple words, in crystalline solids, we can find an orderly arrangement of particles throughout the solid. Examples for crystalline solids are all elements and their compounds. In case of amorphous solids, there is no regular arrangement of particles, or at the most, we can only find short range order. Therefore, in amorphous solids, there is random arrangement of constituent particles. Examples for amorphous solids are rubber, glass, etc. Let's see the characteristics of crystalline and amorphous solids. I'll explain this topic by taking differences between crystalline and amorphous solids, which is very important for your exam. In case of crystalline solids, we can find regular arrangement of particles, whereas in amorphous solids, there is no regular arrangement of particles. These have definite geometric shapes, but amorphous solids have irregular shapes. Crystalline solids have sharp melting points and definite heats of fusion, but amorphous solids melt over a range of temperature and they don't have definite heats of fusion also. Crystalline solids do not give smooth cooling curves, whereas amorphous solids give smooth cooling curves. Crystalline solids are anisotropic in nature. That means they have different properties in different directions. But amorphous solids are isotropic in nature. That means in whichever direction you measure the property, it will be same throughout. Iso means same properties in all directions. Now, when you cut the crystalline solids with a knife, they undergo clean cleavage because their particles are orderly arranged. But in case of amorphous solids, they undergo irregular cleavage as the particles are randomly arranged. Okay, let's conclude the discussion on amorphous solids by knowing their uses. Glass is used in household wares, laboratory wares and in construction field. Rubber, as you know, is widely used in tires, shoe soles, etc. Plastic is used in everyday life. Then there is something called amorphous silica, which is used in making photovoltaic cell. That was about amorphous solids. Coming to the main topic of this chapter, that is crystalline solids, let's see their classification. Based on the nature of constituent particles and the types of bonds present between them, the crystalline solids are further classified into four categories. One is ionic solid. In these solids, the constituent particles are positive and negative ions. Examples are sodium chloride, magnesium oxide, etc. Here we can find ionic bond. Second type is molecular solids. Here the constituent particles are molecules. They are further classified into polar molecular solids and non-polar molecular solids. Polar solids have dipole-dipole interactions. Examples are HCl, SO2, etc. Non-polar molecular solids have London forces between them. Examples are argon, hydrogen, iodine, etc. The third type is covalent or network solids. Here, the constituent particles are non-metal atoms and we can find covalent bonds between them throughout the crystal. Examples are diamond, quartz, etc. The fourth type is metallic solids. All metals and their alloys are examples for metallic solids, and we can find metallic bond in these type of solids. That was about classification of crystalline solids. Let's learn about structure of these crystals. There comes very important term, that is crystal lattice, which is also called as space lattice. Crystal lattice or space lattice is a regular arrangement of constituent particles of a crystal in three-dimensional space. The smallest unit of a crystal lattice is called unit cell. So what is unit cell? It is the smallest three-dimensional portion of a complete space lattice, which when repeated in different directions produces the complete space lattice. What are the parameters of this unit cell? The lengths A, B and C of the three edges and the angles alpha, beta and gamma between these edges. That means, for example, alpha is the angle between edges B and C and so on. So these are the important parameters of a unit cell. Depending upon these unit cell parameters, we have totally 7 crystal systems. Here they are. First one is cubic crystal. Here the three edges are equal. A is equal to B, that is equal to C, and all the three angles are also similar, that is equal to 90 degree. Alpha is equal to beta, that is equal to gamma, that is equal to 90 degree. The second crystal system is tetragonal crystal system. Here A is equal to B, but that is not equal to C. But all the three angles alpha, beta and gamma are equal. They are equal to 90 degree. Third system is orthorhombic or rhombic crystal. Here all the three edges are different, but again the three angles are equal to 90 degree. The fourth system is monoclinic crystal. Here all the three edges are different. A is not equal to B, that is not equal to C. But the two angles alpha and gamma are equal. They are equal to 90 degree, but beta is different. The fifth system is triclinic crystal system. Here all the three edges are different. Similarly, all the three angles are also different and they are not equal to 90 degree also. The sixth type is rhombohedral or trigonal system. Here the three edges are similar. A is equal to B, that is equal to C, and all the three angles are also equal. Alpha is equal to beta, that is equal to gamma, but all the three are not equal to 90 degree. The last crystal system is hexagonal crystal system. Here A is equal to B, but that is not equal to C, and alpha and beta are 90 degree and gamma is found to be 120 degree. So these are the types of crystal systems. Next topic is types of unit cells. We have basically two types of unit cells. One is primitive unit cell or simple unit cell. These unit cells have particles only at the corners. If you consider this as a skeleton of a unit cell, only at the corners we can find particles. That represents a primitive or simple unit cell. Second type is non-primitive unit cell. Under that we have three types. First one is face-centered unit cell. These unit cells have particles at the corners as well as face centers. Second type is end-centered unit cell. They have particles at the corners and any two opposite faces. Third type is body-centered unit cell. They have particles at the corners and one at the body center. I hope types of unit cells is clear to you. As we already studied, in crystalline solids, the particles are closely packed with each other. That means all the unit cells are touching each other. When you have one particle in one of the corners of a unit cell, it will be shared by many other unit cells also. So we will see what is the contribution by particles present at different positions. In a unit cell, if a particle is present at the corner, that will be shared by 8 unit cells. That means the number or amount of the particle that belongs to one unit cell would be 1 by 8. And when the particles are present at the face centers, they are shared between two faces. So the contribution of particle to one unit cell would be 1 by 2. Similarly, when the particle is present at the body center of a unit cell, it completely belongs to one unit cell. It is not shared by other unit cells. That's why its contribution is 1. Then when the particles are present at the edge center of a unit cell, its contribution would be 1 by 4. Based on this, we will calculate the number of particles per unit cell of a cubic crystal. In case of simple cubic crystal, we have particles at 8 corners of the cube, and the contribution by particle at the corner is 1 by 8. So it is 8 into 1 by 8, that is equal to 1. Now in case of a body centered cubic crystal, we have 8 particles at the 8 corners plus 1 at the body center. So 8 into 1 by 8 plus 1, that is 2. Now in case of a face centered cubic crystal, we have particles at the 8 corners, contribution is 1 by 8 plus 6 particles are present at the 6 faces. Each contribute 1 by 2. So 8 into 1 by 8 plus 6 into 1 by 2, that is equal to 4. So these are the number of particles per unit cell of cubic crystal. Crystalline solids are all about closely packed constituent particles. So let's study something about close packing in crystals. We can find different types of close packings in crystals. First type is hexagonal close packing, which is represented by HCP. Here particles are arranged in ABAB pattern. Now the space occupied by the particles in these type of crystals is 74%. The particles are considered to be spheres here. So when spherical things are arranged closely, of course they will leave some empty space between them. So here in case of HCP, the empty space created is 26%. The second type of close packing is cubic close packing, which is represented by CCP. ABC type. The space occupied by the particles is 74% and the empty space generated is 26%. The third type is body-centered cubic system, BCC. Space occupied by the particles is 68% and the empty space is 32%. So it is not a close packing, we can say. Remember students, in simple cubic unit cell, the space occupied by the particles is 52.4%. Let us talk about that empty space, which is also called as void. We can get two types of voids. One is tetrahedral void and second one is octahedral void. Void is nothing but the empty space created when particles are closely arranged. Consider a structure like this in which the particles are arranged, closely arranged like this. So you can find a triangular empty space at the center. So when one more particle is arranged over it like this at the top, you get a tetrahedral void. See students, tetrahedrally the particles are arranged like this. That will create a tetrahedral void, something like this. A simple triangular void surrounded by 4 spheres is a tetrahedral void. Now, a double triangular void surrounded by 6 spheres is an octahedral void. Let's see what is meant by coordination number. It is the number of closest particles or nearest neighbors of any constituent particle. If you are considering an ionic compound, coordination number would be the number of anions present around a cation or number of cations present around an anion. So coordination number in case of HCP and CCP is found to be 12, whereas for BCC it is found to be 8. Remember these values. Now, what are the sizes of these tetrahedral and octahedral voids? Consider a tetrahedral void. Here, 3 particles are arranged in one plane. Now, just imagine one more particle below this plane in a tetrahedral fashion. Now, this represents the radius of the particle. So, radius r of the tetrahedral void would be equal to 0.225 into r, where r is the radius of the spheres in close packing. Similarly, radius of the octahedral void would be equal to 0.414 r. If you have an ionic compound, for cations in the voids and anions in the packing, for tetrahedral, The radius of the cation R plus would be equal to 0.225 into R minus, that is radius of the anion, and for octahedral R plus, that is radius of cation, would be equal to 0.414 R minus. Next topic is number of voids filled and formula of a compound. See students, number of octahedral voids is equal to number of particles present in the closed packing, and number of tetrahedral voids is equal to 2 into number of octahedral voids. Assuming n particles of anions B are present in the packing and 1/3 of octahedral voids are occupied by cations A, then the ratio of A to B would be equal to n by 3 is to n. So that is 1 by 3 is to 1. That is nothing but 1 is to 3. Hence 1 atom of A and 3 atoms of B. That's why the formula is AB3. AB3 would be the formula of a compound. In cubic close packing, total number of voids per unit cell would be equal to 4 octahedral plus 8 tetrahedral, that is 12. In hexagonal close packing, total number of voids per unit cell will be 6 octahedral plus 12 tetrahedral, that is equal to 18. Let's see structures of simple ionic solids. Here is a table. In the first column we have crystal structure. Then what is the arrangement of ions in that? What is the coordination number and formula units per unit cell? So first type is AB type of crystal. Example is rock salt, NaCl type. Here chloride ions are arranged in an FCC fashion, face-centered cubic fashion, and the cation sodium ions are present at the edge centers and body centers. Okay, coordination number of sodium ion here is 4, which means 4 chloride ions are present around sodium ion, 1 sodium ion, and coordination number of chloride is also found to be 4, which means each chloride is surrounded by 4 sodium ions. Formula units per unit cell would be 4. The second example here is cesium chloride type. Here we can find BCC arrangement of particles. The chloride ions are present at the corners and cesium ion is found at the body center. So the coordination number of cesium ion which is present at the center would be 8, and the coordination number of each chloride ion is found to be 8. Formula unit per unit cell is 1. The third example under AB type is zinc blende type, ZNS. This compound follows CCP arrangement. Here sulfide ions have face-centered cubic arrangement and zinc ions are found in the tetrahedral voids. So coordination number of zinc ions is 4, coordination number of sulfide ion is 4. Formula units per unit cell is 4. The second type under this is AB2 type. There are two examples. One is fluoride, CaF2 type. It follows CCP arrangement. The calcium ions have FCC arrangement and fluoride ions are present at all the tetrahedral voids. Coordination number of calcium ions is 8 and coordination number of fluoride is 4. The formula units per unit cell is 4. Second is anti-fluoride, A2B type. Here the anion B2 minus has CCP arrangement and the cations A plus occupy half of the tetrahedral voids. Coordination number of cation would be 4 and coordination number of anion would be 8. Formula units per unit cell is 4. For stability of the ionic compound, each cation should be surrounded by maximum number of anions and vice versa. The number of oppositely charged ions surrounding each ion is called its coordination number. The ratio of radius of the cation to that of the anion is called as radius ratio. If greater is the radius ratio, then larger is the size of the cation and hence greater would be the coordination number. Now the relationships between radius ratio, coordination number and the structural arrangement are given in this table. You can go through this. So as it is evident, when the radius ratio is high, the coordination number is also high and you can see the structures. When the radius ratio is from 0.155 to 0.225, the coordination number is small, it is 3. The structure would be planar triangular, and for radius ratio from 0.225 to 0.414, coordination number would be 4 and it will have a tetrahedral structure. Here is the example. From 0.414 to 0.732, coordination number would be 6. It will have octahedral structure. Example, rock salt, NaCl. From 0.732 to 1, radius ratio, coordination number would be 8. It will have a body-centered cubic structure. Cesium chloride is an example. Next important topic is calculation of density of a cubic crystal from its edge. For cubic crystals of elements, density rho is given by rho is equal to Z into M divided by A cube into N naught into 10 to the power minus 30, where Z represents number of atoms per unit cell and M represents atomic mass of the element, N naught is Avogadro number and A is the edge length of the cube in picometer, and rho represents density of the crystal in gram per cm cube. Now, if edge A is given in centimeter, then the formula used would be rho is equal to Z into M divided by A cube into N naught. In terms of SI units, M is in kg per mole and A, edge length, is in meters. Then rho is in kg per meter cube. So this is the unit. For cubic crystals of ionic compounds, Z would be equal to number of formula units per unit cell and M would be formula mass. Remember students, for ionic compound of the type A plus B minus having FCC structure, for example NaCl, edge A, edge length A is equal to 2 into distance between cation and anion. Okay, the next important topic is imperfections or defects in solids. As we know, crystals have orderly arrangement of particles in them. So any deviation or any departure from the perfectly ordered arrangement of constituent particles in a crystal is called defect or imperfection. Basically, there are two types of imperfections. First one is called as stoichiometric defect. Second one is called as non-stoichiometric defect. So let's see what is meant by stoichiometric defect. When ratio between cations and anions remains the same, you can call it as stoichiometric defect. Under that, we have two more types. One is Schottky defect, second one is Frenkel defect. Now I will explain both these defects by taking the differences between them. This is again another important question from the exam point of view. So let's see the differences between Schottky defect and Frenkel defect. In case of Schottky defect, equal number of cations and anions are missing. But Frenkel defect is observed when cations are missing from lattice sites and occupy the interstitial sites. Schottky defect occurs in compounds with high coordination number and in those compounds which have just small difference in the size between cations and anions. But Frenkel defect occurs in compounds with low coordination number and also those which have very large difference in the size of cations and anions. We will see some examples. The compounds which show Schottky defect are sodium chloride, potassium bromide, silver bromide, cesium chloride. And some of the compounds which show Frenkel defect are silver chloride, silver bromide, silver iodide. As you can see, silver bromide shows both Schottky defect and Frenkel defect. Because of Schottky defect, density of the solid decreases. But because of Frenkel defect, there is no effect on density. So these are the differences between Schottky defect and Frenkel defect. I hope it is clear to you. So let's understand the meaning of non-stoichiometric defects. When ratio of cations and anions changes as a result of the defect, you find non-stoichiometric defect. You further have three types under non-stoichiometric defects. One is metal excess defect, second one is metal deficiency defect, third one is impurity defect. Let us study one by one. Metal excess defect. It can happen By two ways. First one is by anion vacancies. Second one is by presence of extra cations in the interstitial sites. Let's see the first one, that is by anion vacancies. On heating sodium chloride in presence of sodium vapor, some anions, that means chloride ions, leave the lattice sites of the crystal, and those sites are occupied by electrons, and these sites are called as F centers, so they give color to the crystals. Second one is by presence of extra cations in the interstitial sites. Let's take an example. On heating zinc oxide, oxygen gas is lost from the zinc oxide crystal. So Zn2 plus ions and electron occupy the interstitial sites. The next type of non-stoichiometric defect is metal deficiency defect. This occurs where metal shows variable valency. Let's take an example. 2A plus ion in lattice sites may be replaced by A2 plus ion, one A2 plus ion in one lattice site, and other lattice site remains vacant. The third type is impurity defects. It is possible to add impurities to crystalline solids to change their properties, and that process is called as doping. Let's see how does it happen in ionic solids by taking an example. Strontium chloride is doped into sodium chloride so that two Na plus ions are replaced by one Sr2 plus ion, producing one cation vacancy. How to do doping in covalent solids? First one is by doping with electron-rich impurities. For example, group 14 elements like silicon or germanium can be doped with group 15 element like phosphorus, arsenic, etc. At that time, free electrons become available, which increases the conductivity of the substance. Now, such solids are called N-type conductors. That is one way of doping in covalent solids. Second way is by doping with electron deficient impurities. Let's take an example. Group 14 elements like silicon or germanium can be doped with group 13 element like boron, aluminium or gallium. As a result, holes are created. At that time, what happens? Electrons move to occupy the holes. These holes move towards negatively charged plate as if they carry positive charge. These are called p-type semiconductors. So when you dope with electron deficit impurities, you get p-type semiconductors, and when you dope with electron rich impurities, you get n-type semiconductors. The term hole comes in p-type semiconductor, and remember the elements also. Let's see the conductivity values of conductors, insulators and semiconductors. Conductors show the conductivity of 10 to the power of 4 to 10 to the power 7 per ohm per meter, and insulators 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. Semiconductors show a conductivity of 10 to the power of minus 6 to 10 to the power 4 per ohm per meter. The next important theory regarding conductivity is band theory. In case of a metal, the atomic orbitals of the metal atoms are so close in energy that they overlap to form a large number of molecular orbitals very close in energy. It can be shown something like this. Here, the lower half may be filled with electrons and the upper half may be empty. Or we can say two sets of molecular orbitals are formed. The filled molecular orbitals with lower energy form the valence band. So this is valence band, and the empty or partially filled molecular orbital with higher energy form the conduction band. So this is the conduction band. Based on band theory, let's see the distinction between metals, insulators and semiconductors. Here is a picture which shows the different types of bands in metals, insulators and semiconductors. So consider this one for metals. Metals have either only valence band, that is the lower half which is filled and the upper half which is empty, or there could be a partial overlap between the filled valence band and the empty conduction band, a slight overlapping. Now for the insulators, there is a very large energy gap between valence band and the conduction band. Whereas for semiconductors, there is just a small energy gap between valence band and the conduction band. I have written the same thing here. Metals have either only valence band, in which the lower part which is filled with electrons and the upper part is empty, or there could be a slight overlap between the filled valence band, lower band, and the upper empty conduction band. Whereas in case of insulators, between the two bands there is large energy gap. Whereas for semiconductors, there is just a small energy gap between the lower valence band and the upper conduction band. Okay students, now let's see the classification of substances on the basis of magnetic properties. On the basis of magnetic properties, the substances are classified into 5 types. They are diamagnetic substances, paramagnetic substances, ferromagnetic substances, antiferromagnetic substances, and ferrimagnetic substances. Let's study them one by one. The substances which are weakly repelled by the external magnetic field are called diamagnetic substances. Examples for diamagnetic substances are titanium oxide, water, sodium chloride, benzene, etc. They contain fully filled orbitals and hence they have zero magnetic moment. They do not have unpaired electrons. Paramagnetic substances are those which are attracted by the external magnetic field. Example, oxygen, Cu2+, Fe3+ ion, Cr3+ ion, etc. Their atoms, ions or molecules contain unpaired electrons, and that's why a net magnetic moment will be there. They lose their magnetism in the absence of external magnetic field. The third type of substances are ferromagnetic substances. They show permanent magnetism even in the absence of magnetic field. For example, iron, nickel, cobalt, gadolinium, chromium oxide, etc. This is because when placed in magnetic field, their unpaired electrons or the magnetic domains get permanently oriented in one direction. So that's why they have the permanent magnetic moment. Now there are antiferromagnetic substances. They are expected to possess paramagnetism or ferromagnetism but actually have zero net magnetic moment. For example, manganese oxide. This is because of equal number of magnetic domains in opposite direction. So they cancel with each other. The fifth type of substances are ferrimagnetic substances. These are expected to have large magnetism but actually have small net magnetic moment. For example, magnetite and ferrites. This is because of unequal number of magnetic domains in opposite direction. Finally, we have Curie temperature. It is the temperature above which a ferromagnetic substance shows no ferromagnetism. Okay students, so that was about a quick revision of chapter solid state. For detailed explanations and derivations, you can go through the textbook. So thank you so much for watching.